All right, 3.5, predicting equilibrium positions. If we take any acid-base reaction, like this one here, we have, what do we have? Well, we've got an acid, and then we have a base. We have our conjugate base, and we have our conjugate acid. Well, the whole question that we want to answer is, with respect to this equilibrium, which side does it lie to? We've got two ways to predict this, don't we? We can either use pK values, okay, for the acid and the conjugate acid, and then we can say, well, the higher pKa, which is the weaker acid, the equilibrium is going to lie to that side. So that's one way of solving the problem. And if we don't have pK values, or if you've maybe forgotten the pK values, you can just look at the relative stability of the bases, the base and the conjugate base. And for that, we would use Areo. Okay? We'd look at the conjugate base, and then we'd evaluate the stability of the negative charge in terms of the atom, resonance, induction, and orbital. So with that in mind, let's take a look at a problem. This is problem 3.27 from your textbook. We have an equilibrium arrow here, but it's asking us which side does it lie towards, to a greater amount. Is it lying towards the reactants over here, or is it lying towards the products over here? Well, again, we've got a couple of ways of doing this. We can start by labeling the acid, which in this case is ammonia, and this would be our base. Over here, this is our conjugate acid, and this is our conjugate base. And then we can take a look at the pKa of the acid and the conjugate acid. This is ammonia. If you go to table 3.1, that's the table with the pKa values that I asked you to memorize. And the pKa of ammonia is 38. So there's the pKa of our acid. The pKa of butane, again, this molecule is an alkane. It only has sp3 hybridized carbon-hydrogen bonds. Okay, so every bond to hydrogen is an sp3 hybridized carbon-hydrogen bond. And we know that the pKa for those types of bonds is around 50. So which is the weaker acid? Is it the ammonia or the butane? Well, we know that the higher the pKa, the weaker the acid. And so our equilibrium is going to lie to the side of the product. So the equilibrium should lie to this side like that. Okay, so that's one way of doing it. The second way would be Areo, right? If we look at the two bases, we have this base, and I'll just circle the part with the negative charge, and then we have this base over here. If we try to use Areo, well, we can use atom, can't we? Because the negative charge in the first one is on a carbon, right? Negative charge on a carbon, and here the negative charge is on a nitrogen. Well, carbon and nitrogen are both in the same period, aren't they? We have boron, carbon, nitrogen, oxygen, fluorine. And we know that the electronegativity increases as you go across a period. Nitrogen is more electronegative, and so its base, or the base with the negative charge on the nitrogen, I should say, would be more stable, right? So most stable base based on Areo. And of course, all we had to do was look at the type of atom, and we were able to solve the problem. So there you go, two different ways of solving the exact same problem. All right, let's try a different one. So if we were to look at something like, let's see, do I have some room on here? Yeah, I do. Okay, maybe I don't. Yeah, I've got a little bit of room here. I can just erase some things. There we go. So I'll give you another example. Let's say we had this kind of reaction. So we've got phenol like this. And just imagine you're on a quiz and you're faced with a problem like this: phenol plus a hydroxide. And we have equilibrium arrows. And we have the phenoxide, which is this. And then we have water. So the same thing. I want to know which side, or to which side, does the equilibrium lie? Well, again, we could use the same rationale here, right? This is our acid. This is our base. This is our conjugate base. And this is our conjugate acid. Well, if you compare the pKa's of the two acids, the pK of phenol is 10, and the pK of water is 15.7. So which one is a weaker acid? Water is a weaker acid. Therefore, the equilibrium is going to lie to the side of the products in this case. So that's one way of solving the problem. And could we solve this problem using Aereo? Absolutely we can. Now we're going to look at this base, and we're going to look at the conjugate base. Can we solve it using atom? No, because the negative charge is on an oxygen in both cases, but we can solve it using resonance, because this base has no resonance contributors, contributors, whereas here we have 3 resonance contributors that we could draw, right? And you should be able to draw those with relative ease, starting with the curved arrows like that. So again, we were able to solve this one using pKa values, and we were also able to solve it using the concept of Aereo. And so both methods can be used. So with that in mind, I want to talk about choosing reagents, because you're going to be asked to choose quite a few reagents to come up with different syntheses in this class. It says another important skill is to be able to choose an appropriate reagent for an acid-base reaction. So what it's asking you here is if you were to have these 4 bases, okay, so there's 4 different bases on here. Okay, so we'll kind of divide that up into 4. It says choose an acid from table 3.1 that could effectively protonate each of the following molecules. Well, this one here is called an acetylide, and we're going to see that a lot in chapter 9 when we talk about alkynes. If you were to take that acetylide and treat that with water, would that effectively protonate the acetylide ion? I say it would, and I'll show you why. Because you'd end up with this molecule, acetylene, and you'd have the proton, and yes, there's another one over here, but anyhow, I'm kind of running out of space, so I'll just put that one. And then you'd also be left over with the hydroxide. Now, again, you could solve this using pKa's. The pKa of water is 15.7. The pKa of the sp hybridized carbon-hydrogen bond is around 25. And so since 25 is greater than 15.7, our conjugate acid is weaker than the water, which is behaving as an acid, the equilibrium is going to lie to this side. Okay, that's one way of solving it. Could you solve it using Aereo? Well, if you look at the stability of the 2 bases, right, whether it's the acetylide or the hydroxide, yeah, you could solve it using Aereo. Right, if you write down ARIO, you can solve it using atom, because here the negative charge is on an oxygen, here the negative charge is on a carbon. Oxygen is more electronegative, so again, using Aereo, we also proved that the equilibrium is going to lie to the side of the products. And so water would be effective at protonating the acetylide. Okay, let's take this next one here. What would be an effective agent to protonate the conjugate base of a ketone? Well, in that case, a good acid would be something like hydronium. Let me show you why. When we draw the ketone out plus our water molecule, this is our acid, the hydronium. It has a pK of around 1.7. Okay, the pK of our conjugate acid is around 19. Well, which side is the equilibrium going to lie to? It's going to lie to the side of the weaker acid. So again, my equilibrium is going to lie to the side of the products. And so hydronium would be more than effective at protonating this anion right here. So hydronium would be a good choice in this case. Let's take a look at the next one. So we have an acetate ion. A good agent to protonate this, for example, might be something like HCl. Right, let's say we combine that with hydrochloric acid. Well, hydrochloric acid has a pKa of -7, and what you end up producing would be acetic acid, which has a pKa of around 5. I know in the table it says 4.75, but that's neither here nor there. And then we have the chloride ion. So again, the equilibrium is definitely going to lie to the side of the weaker acid. So HCl would be effective at protonating the acetate ion. Could we use aereo? Absolutely. Remember, it would be a little tougher here in this case because chlorine is less electronegative than oxygen, but chlorine is in the third period. So since it's a little bit, or it's actually significantly bigger than the oxygen, it's going to be better at stabilizing that negative charge like that. And then for the last one, if you want to protonate that, just protonate a ketone to make the protonated carbonyl, you'd have to use a really strong acid like sulfuric acid, right? Because then you saw the protonated carbonyl that I showed you earlier today has a pK of around 7. It's like 7.3 or something like that. So 7.3 is what we'll put here. And the pK of sulfuric acid is -9. And when I said 7.3, I meant -7.3. There you go. So these are really acidic, right? And then you'd have the hydrogen sulfate ion over here. Oops. Sorry, I'm having a problem with my computer. Just give me a second. Come on. There we go. Yeah, so in this case, you'd have to choose something extremely acidic, like sulfuric acid. Anyhow, that's the kind of rationale that we want to have. And the whole point behind doing this exercise is twofold, in my opinion. It's first of all showing you that all of the acids that we chose, water here, hydronium here, hydrochloric acid here, sulfuric acid here, the whole point behind this exercise is first of all, realizing that the acid that you choose has to be stronger than the conjugate acid that's formed, right? Because you want the conjugate acid to be weaker is another way to frame it. So there's that. And I think the second take-home message from this slide is that you've got to have a good knowledge of table 3.1 and of the aereo concept. In order for you to really master this chapter and to be successful in organic chemistry, you can't just say, well, I'll just memorize the pKa's and I'll forget about aereo. Or you can't just say, I'll learn aereo, but I'm not good with numbers or memorizing numbers, so I'll forget the pKa's. You'd have to have a good understanding of both of those. Section 3.6 deals with what's called the leveling effect. And follow along with me here. It says another important skill is to be able to choose an appropriate solvent for an acid-base reaction, right? You think about virtually all of the acid-base reactions that you would have done in general chemistry too. They were pretty much all done in water, right? Everything was done in water. Well, what you're going to see in organic chemistry is, do we do reactions in water? Absolutely. Absolutely we do. But we're going to see many, many, many reactions in organic chemistry that aren't done in water and can't be done in water. And there's a good reason for that. There are quite a few reasons for that. But anyhow, it says here the solvent, it says, should be able to surround the reactants and facilitate their collisions, right? Which, of course, causes reactions. But you can't have a reaction with the solvent, right? That's not going to work. If the solvent reacts, well, that destroys the whole purpose of doing the reaction. Now, water is an interesting choice of solvent. Why? Because water is amphoteric, meaning it can behave as an acid or a base, depending on the situation, right? It always depends on where water is. It has what's called a leveling effect on very strong acids and very strong bases. Now, here's something that you probably would have seen, or you should have seen in general chemistry too, but you might not have seen it framed this way, is that an acid stronger than hydronium, right? Hydronium has a pKa of -1.73. So we'll put -1.7. But if you have an acid stronger than hydronium, it can't be used in water. And if you're thinking, well, what? That's not true. Mr. Dion, I use sulfuric acid in water all the time in general chemistry. We'd say sulfuric acid in water, blah, blah, blah. You know, we talk about putting sulfuric acid in water, and we talked about how you shouldn't mix, acid and water is a good thing. Water and acid is dangerous, right? We talked about putting acids in water. Why couldn't I use them? Well, what it's saying here, or what this means, is that if you put an acid stronger than hydronium in water, you don't have any of that acid left over, or you're going to have not much of that acid depending on it. Also, if you have a base stronger than hydroxide, it can't be used in water. Why? Well, let's explain why. If you didn't follow me on this bullet point here, let me explain why. And this is something that you might not have thought of before. But let's say we have an acetate ion. Okay, this is called an acetate ion. You would have seen this in general chemistry too, for sure, the acetate ion, okay, when you talk about buffers, right? You talk about the Henderson-Hasselbalch equation. Well, if you put acetate in water, what do you actually have? Okay, here's my acetate ion. You put it in water, and acetate can behave as a base, and it's showing water acting as an acid here. Well, then you'd produce acetic acid and hydroxide. Even if you didn't know the name of anything on here, even if you didn't know the name of water, look at the relative pKa's. The pKa of water is 15.7. The pKa of acetic acid is around 5. So generally speaking, when we have a difference in, I'd say, about 10 pKa units, okay, that would mean that we can use this as a solvent, okay, because the equilibrium is going to lie mostly to this side, right? This is the weaker acid. Okay, I'm going to have very little of this in solution. What's your point, Mr. Dion? I'm not following you. What it means is, let's say you have the acetate ion. I should switch over to a different color. If you have an acetate ion, which is this guy right here, okay, it's going to react with water to some extent, but the equilibrium is mostly going to favor this side over here. And so water, the whole point of this slide is nothing more than this. It's telling you that water is an okay solvent to dissolve an acetate ion. Okay, acetate usually comes as a salt in sodium acetate. So you'd have sodium plus CH3, CO2 minus. Sodium acetate. If you dissolve sodium acetate in water, it's going to remain intact. Okay, you're going to form a little bit of this, but not a whole lot. Now, if we switch over to something where the leveling effect does come into play, what if you take sulfuric acid and put it in water? Okay, if you walk over to a bottle of sulfuric acid in a lab, okay, if you walk over to the shelf and you see a bottle and it says, you know, H2SO4 dissolved in water, it says sulfuric acid on it. Well, there's actually almost no sulfuric acid in there. What? Yeah, there's very little sulfuric acid in there based on what's called the leveling effect, right? Because you're putting in water, water can behave as an acid, but when water is the solvent in which sulfuric acid is dissolved, the water is going to behave as a base, and it's going to accept a proton from the sulfuric acid. What happens if you compare the pKa's of hydronium and sulfuric acid? Look at the difference. Sulfuric acid has a pK of 9. You put it in water, you end up forming hydronium, which only has a pK of -2. That's a difference of 10 to the power of 7. Okay, so what's that? 10 million times. So hydronium is 10 times weaker of an acid than sulfuric acid. What is that? What's the whole point? Is that the equilibrium is mostly going to lie to this side. Okay, are you going to have some sulfuric acid intact? Sure. 1 in every 10 million molecules, right? But in other words, when you have an aqueous solution of sulfuric acid, or hydrochloric acid, it's really just a solution of hydronium. All right. The main difference between concentrated sulfuric acid and dilute sulfuric acid is the amount of hydronium that's in there. And if you've never thought about that before, well, you're thinking about it now. So that means that if I put sulfuric acid in water, I mostly have hydronium. Kind of interesting, huh, when you think about it? And we're going to look at the consequence of that right now. It says here, because water can act as an acid or a base, it has this leveling effect. So let me show you a particular example here. Okay, it says bases stronger than hydroxide cannot be used in water. For example, you wouldn't be able to perform the following acid-base reaction in water. Let me show you what I mean. Right? Remember, general chemistry, you did every reaction basically was done in water. Okay, but what I'm telling you is that in organic chemistry, you're going to run into many scenarios where it won't work. If you try to do this reaction in water, okay, let me tell you, my friend, it's not going to work. Why? Why won't it work, Mr. Dion? Let me show you. Because you don't have any water left over, and you're going to end up destroying this compound here, which is called dimethylamide. Let me show you what would happen. Let's think about it. If you had amide, okay, so that's this guy right here. I'm just drawing in both of the lone pairs. If it's in water, okay, let's draw the structure of water. What's the possible acid-base reaction that could occur, right? This could behave as a base. Water can behave as an acid. And this base, if it extracted the proton, and we're just talking hypothetically right now, okay, we'll draw equilibrium arrows. What would you end up with? You'd end up with this. You'd end up with this, which is an amine. You know that amines have a pK of around 38. So let's just write pKa is equal to 38, plus you'd be left over with hydroxide. Well, what was the pK of water? The pK of water was 15.7. If you take your calculator and you take 38, subtract 15.7, you've got a difference of 10 to the power of 22.3. So let's just shorten it to 22. But that means that water is 10 to the power of 22 times stronger of an acid than this amine. What is that telling you? The equilibrium is going to lie completely to this side. It's such a big difference in pKa. Okay, so what that means is that as soon as this base sees the water, it's going to get destroyed, and you're going to have none of it left. You're only going to have this. And so the take-home message is that this base is stronger than hydroxide. Okay, and so you can't do a reaction in water when your base is stronger than hydroxide because it's going to ruin the reagent, right? It says right here, base is stronger than hydroxide, cannot be used in water. Kind of interesting, huh? And it's something that you maybe haven't thought of before. And if you're wondering, well, then what do I use as a solvent, Mr. Dion? You tell me the answer. If I can't use water, what would I use? Well, we'll talk about that even more later on. But an appropriate solvent for this might be something like hexane. If you're wondering, what the heck is hexane? Well, hexane would be this. So you have 1, 2, 3, 4, 5, 6 carbons like that. That's a liquid at room temperature. And I know there's not a lot of room on these slides, but I just want to show you quickly. Let me just kind of scribble it up here in the notes and see if you can follow along with me. If you were to take that base, that amide, let me write it in blue ink, okay? Where's my blue pen? There we go. If you were to take that amide, let me just make it a little prettier here. If you were to take that amide, okay, and you put it in hexane, there's hexane. Okay, which side is the equilibrium going to lie to? Here we have this, plus you have the conjugate base left over like that. Well, the pK of all these sp3 hybridized carbon-hydrogen bonds is 50. The pK here we said was around 38, right? So the equilibrium is going to lie hard to this side. Okay, you get a difference of 10 to the 12. And so hexane would be an appropriate solvent because this reaction is not going to occur. It's not going to give you these two products. So in this case, you can put that Drake meme, where he has the hands up like, no for the water, but then, yeah, for the hexane. Hexane would be an appropriate choice of solvent there. Anyhow, just something interesting, the leveling effect. And if you're wondering, are you going to ask us about solvents on the next quiz? Absolutely. I could ask a question, would this be an appropriate solvent for this reaction, and of course, what are we doing? Here, all we're doing is looking at pKa values and Areo again, and really just extrapolating on it a tiny bit, okay? Now, if you're a really astute student, and I know that you all are, I bet you there's a question that's been burning in your mind ever since I showed you the difference in pKa between these two alcohols. I remember earlier on today, I asked you a question and some students said like, oh, an alcohol, an alcohol is more acidic than an amine or something. So my students picked it up really quickly that alcohols are relatively acidic, compared to things like alkanes, alkenes, alkynes, okay? But if you look at these two alcohols, remember these were specifically in table 3.1. In table 3.1, you find these two, right? And there is a difference, right? This is 100 times more acidic than this compound, right? Because it's got a lower pKa. You can't use Areo here, can you? Let's think about it. You got atom, resonance, induction orbital, right? If you were to draw the conjugate base of both of these, you'd have the negative charge on an oxygen. There's no resonance structure to draw. There's no induction, and the orbital would be the same. How would you explain the difference in acidity between these two? Why is this a stronger acid? It's got to have something to do with the conjugate base that's formed, doesn't it? And it absolutely does. Let me find my slide here. But it's got to have something to do with this, right? Versus this. Okay, it's got to have something to do with the relative stability of their conjugate bases, and you would be 100% correct in assuming that. Let me show you the answer, and it's not a really complex answer. Again, I don't think it's simple, because nothing in organic chemistry is simple, but it's not a super complex answer. Here we have the conjugate bases shown. I don't know why there's no negative charge. What kind of hobo put that together? Anyhow, there you go. So there's a conjugate bases of the terbutanol and the ethanol. So terbutoxide and ethoxide, right? If this one is more acidic, right, the conjugate base must be more stable in order for ethanol to be more acidic. And the answer is this. It's because of the interaction of the solvent and the alkoxide, or the negative charge on the oxygen. And it's the ability of the solvent to stabilize that negative charge. Since the terbutoxide is sterically hindered because of all these CH3 groups over here, all these methyl groups, it kind of blocks the oxygen, and the oxygen has a harder time interacting with solvent molecules. It can interact with them, but it interacts with less of them than the ethoxide, which only has this one little measly group. And so more solvent molecules can gather around it and stabilize that negative charge. That's the answer, my friends. Nothing more than that. Is that here you've got the delta negative on the oxygens, and more of the solvent molecules can kind of gather around with their dipoles if it's polar, or temporary dipoles if it's non-polar, right? Or yeah, and there you go. That's it. Give me a thumbs up if you just follow me on that concept of the solvating effect. And this is really the only solvating effect that we look at in this chapter. Does everybody follow me on the solvating effect of why ethanol is more acidic than terbutanol? You'll find that this chapter has a few little examples like that, where it's kind of just selective examples that are very important because they come up, sort of over and over in organic chemistry. You see a lot of the same things coming up in the class many times. Keep jumping around on my slides here. There we go. All right, so let's talk about counter ions. You notice that there's only one slide for section 3.8, maybe the shortest section we ever look at in this class. So one slide devoted to counter ions. Do you guys remember from general chemistry writing out complete ionic equations, right? So first you'd write out a molecular equation, or then you'd write out a complete ionic equation, then you'd write out a net ionic equation. Remember that, the NIE? Well, if you remember the net ionic equation, you would end up canceling spectator ions, so ions that didn't participate. Like, say, for example, you looked at a metathesis reaction or a precipitation reaction, you'd cancel out those ions. Well, you've probably noticed that in organic chemistry, we write out stuff like this all the time, like this reaction down here. There is no cation, right? There's no such thing as a negative charge just floating around in a solution unless it's balanced out by something. Well, counter ions, which are usually cations in organic chemistry, not always, but those are called spectator ions. And even though they are present, we leave them out almost all the time in organic chemistry. So let's say you had this reaction right here. You've got sodium amide plus water gives you ammonia plus sodium hydroxide. Since if you wrote this out into its ions, right, this is ionic. You've got sodium amide plus water gives you ammonia plus sodium plus and hydroxide minus. Since the sodium is the same on both sides, we leave it out. Okay, and all you're left over with is the net ionic equation. So everything that ends up being changed. So to put it really just succinctly, counter ions are mostly left out in organic chemistry because they don't play a role in the reactions. Are there reactions that we're going to look at where we see counter ions playing a role? Sure, yes, some. But I'd say they're the vast minority. And if there's something really important that I want you to know about the spectator ion, I would let you know. Okay, I would totally point that out to you and say it's important in this case. But there you go. So that's counter ions. And this section really, in my opinion, it's more like answering a question for my students, because every once in a while I'll teach this class, usually when it's face-to-face, and somebody will raise their hand and be like, where are the positive charges? How come they're left out? You keep drawing everything with just negative charges. I mean, really, if we go back into the slides today, look, everything here, you have either all positive charges or all negative charges. Maybe that wasn't a good example, but here we have negative charge and negative charge. We don't have any, right? Positive charges left out. So you see that all the time in here, right? We have negative here and negative there. All right, so we leave out spectator ions all the time in organic chemistry. It's just something that okay, well, let's get into the last section of chapter 9, which deals with Lewis acids and Lewis bases. So if you took General Chemistry 2 recently, you might remember that there's actually 3 definitions of acids and bases. We started it with Bronsted, didn't we, in this chapter? But the first one actually was the Arrhenius definition of acids and bases. And what Arrhenius said was that an acid is something that produces H plus, and he said a base is something that produces OH minus. But the problem with that definition, with the Arrhenius definition, is something like ammonia is a base, but it doesn't have hydroxide in it, right? He was just thinking about things like sodium hydroxide, potassium hydroxide, lithium hydroxide, calcium hydroxide, you know, those kinds of compounds. So Bronsted-Lowry came along, right, and they kind of blew the lid off that. So Bronsted-Lowry, we said that an acid is an H plus donor, and that a base is an H plus acceptor. But the problem is that there are acids and bases that don't fit the Bronsted-Lowry definition either. And you're like, what? Yeah, there are. There are some that don't fit this definition. Let me show you what I mean. So the Lewis acid-base definition, all it does is serves to broaden our definitions of acids and bases. And I'm going to show you why. So according to Lewis acid-base theory, a Lewis acid is something that accepts electrons, and a Lewis base donates electrons. So the way that I remember this is the acid, where's my pen? There. The acid accepts electrons, right? Those are all vowels. Acids accept electrons. And I say that the base donates electrons. So here you've got AA and here you've got BD. I don't know. That's the way I find it's easy to remember it that way. Right? Acids accept electrons, bases donate electrons. I mean, whatever you have to use to help you rationalize that will work. But what's cool about this is that acids that fall under the Bronsted-Lowry definition, everything that we've looked at today up until right this second, also fall under the Lewis acid-base definition. Okay? Bases under the Bronsted-Lowry definition, they're also bases under the Lewis definition. And so again, the Lewis acid-base definition just serves to broaden the definition of an acid and a base, right? If we were thinking about Bronsted, so let's write Bronsted-Lowry, we'll put BL up here, right? This would be our acid. Acid. This water is behaving as our base. This is our conjugate acid, and this is our conjugate base, like that. Okay, well, let's think about what an acid is. It says, according to Lewis, it says that an acid is an electron acceptor. Well, if this is our acid, it's accepting the pair of electrons from the pi bond, isn't it? So this is our Lewis acid, so this is also an acid. The base is the electron donor, right? The water is donating this pair of electrons to the acid. So here's our base, right? Our conjugate base is also a Lewis base, because if we think about the reaction in reverse, it would be donating a pair of electrons to this proton. I'm going to take that out. So this would be a base, and this would be an acid because it's also an electron acceptor, right? It's taking this pair of electrons, going backwards. Anyhow, there you go. So Lewis acids and bases. So something that you can imagine you're going to be asked to do on your next quiz would be identify Lewis acids and Lewis bases. Now, water and hydrochloric acid, those, again, they fall under the Bronsted-Lowry definition, don't they? There's no problem there. There's no issue with that whatsoever. But what if we look at something that's a little bit more complex? It says here in the slide that some acid-base reactions can't be classified using Bronsted-Lowry, and that's why you need to know Lewis acid-base. So on the last slide, and I know you weren't doing this, but if you're thinking, well, jeepers, if it's the same as Bronsted, why do I even need to know this? Because there's examples that won't fall under the Bronsted-Lowry or the Arrhenius definition. Take a look at this reaction here. This is an acid-base reaction, right? We have our water, which is acting as a base here. Is it accepting a proton? No. I don't see it accepting a proton over here. I don't see a hydronium. This is our acid. According to Bronsted-Lowry, is the boron trifluoride acting as an acid? Is it donating a proton? Hell no. I don't see it giving up a proton. But does it follow Lewis acid-base theory? Oh yeah, it does. Right? This is our base. It's an electron donor. Right? Boron trifluoride has that empty, unhybridized p orbital. Is it behaving as an acid? Absolutely it is, right? Son of a gun. This is our acid. It is our electron acceptor. Okay, it's taking the pair of electrons over here. So there we go. Lewis acid-base theory is a necessity. You have to know Lewis acid-base theory. Well, with that in mind, let's take a look at a question where we're looking at Lewis acid-base theory. So this is question 3.32, straight out of your textbook. It says, in each case below, identify the Lewis acid and the Lewis base. And Mr. Dion's going to throw one in there. Let's add to it and draw curved arrows. So I'm going to give you a few seconds to look at this one. I'm going to go grab a drink of water, and I want you to try to draw the curved arrows, identify the Lewis acid, Lewis base here, and identify the Lewis acid, Lewis base here.
Hey, Daddy.
Hey, what's up? Dad's in class right now. Okay. Okay, I know I'm not talking right now. I'm teaching my class. What's up?
I just wanted to come and say hi.
Okay. I'm going to come up and see you in a few minutes, okay?
We're not in the house. We're outside.
Okay, I'll come outside and see you in a little bit, okay?
I was holding a potato bag, and it kept pooping on my hand.
Okay, well, make sure to wash your hand, okay, honey? All right. Okay. Well, let's take a look. Yeah, sorry. Sometimes my kids just come down and interrupt me. By the way, during our last break, I went upstairs and they had busted into my daughter's 6 and she learned how to climb into the pantry and climb up the shelves. My wife keeps a box of candy up there, which is supposed to be off limits. They had the whole thing open on the floor, so that's why. Ugh, the fun doesn't stop. Anyhow, yeah, so let's take a look at this first one. So this is 3.32a. If I call these two species here, if I call them 1 and 2, could anybody identify which one is the Lewis acid? And it's not a trick question. Yeah, it's the second one that's the Lewis acid. The second one is the Lewis acid. Why? Because it's the electron acceptor. If you look at what's changed when we make this intermediate here, this is the bond that's being formed. It's this one that I'm circling in yellow. And so if you draw the curved arrows for that, right, the ketone is donating the electrons and the aluminum is accepting the electrons. So number 2, this is the Lewis acid. And number 1 is the Lewis base. Lewis base. Okay? So remember, another way that might be helpful to think about that is that aluminum is in group 3A. So it's got an empty p orbital, an hybridized p orbital that can accept electrons. That might be something handy for you. The next one, I see that whoever drew this left out a bunch of lone pairs, and that was the author of our textbook who left them out deliberately, just so you would get some more practice. Practice makes perfect, right? Okay, let's see here. We've got a ketone. We've got a hydronium here. If I call these, I don't know, I'll call these 1 and 2 as well in blue ink. Could anybody tell me which one of these would be the Lewis acid? Yeah, absolutely. It's the one that's behaving as the acid, isn't it, Bruna? Yeah, 100%. You're all correct. Absolutely, right? The ketone is donating the electrons to this proton, and then the Lewis acid is accepting this pair of electrons. So this is our Lewis acid, and this is our Lewis base. Like that. There you go. Remember that a Lewis acid is an electron acceptor, and a Lewis base is an electron donor. And again, that's going to come up over and over and over in organic chemistry because we're just laying the ground, kind of the groundwork for the course right now. And that covers all of the content for chapter 3. That is all of the acids and bases chapter.